Welcome to the demonstration of PRISM, a digital twin-empowered proactive interference management approach for spectrum sharing in Internet of Vehicles networks. As autonomous vehicles become increasingly interconnected with each other and network infrastructure, the challenge of efficiently managing the vast data streams they generate becomes even more critical. Internet of Vehicles, or IoV, leverages multiple communication modalities, including vehicle-to-vehicle, or V2V, vehicle-to-infrastructure, or V2I, vehicle-to-pedestrian, or V2P, and vehicle-to-cloud, or V2C links, to ensure timely, reliable information exchange. However, this densely interconnected environment also introduces significant co-channel interference, necessitating advanced radio resource management. Modern vehicular networks require large bandwidth to support the high data volumes generated by integrated sensors and infotainment systems. In dense IoV environments, spectrum sharing is essential to maximize the utilization of licensed bands. Unfortunately, sharing spectrum among neighboring vehicles inherently leads to co-channel interference, which degrades network performance. Furthermore, as the channel in vehicular networks ages rapidly due to high mobility of the vehicles, traditional radio resource management schemes may struggle to adapt to such dynamic scenarios and suffer from outdated scheduling decisions. To overcome these challenges, we propose PRISM, an advanced radio resource optimization framework designed to proactively mitigate co-channel interference in dense IoV networks. Unlike conventional optimization schemes, PRISM accurately predicts vehicles' communication channels and proactively allocates radio resources, thereby minimizing the deleterious impact of outdated scheduling decisions. This unique capability stems from the awareness of both static and dynamic network contexts, including vehicle mobility, geolocations and antenna configurations of roadside units, and the 3D electromagnetic environment that influences RF propagation in the network. PRISM is a centralized radio resource management scheme hosted within a mobile edge computing center. The framework is structured around three core engines. The location prediction engine tracks and forecasts vehicle positions based on historical position data stored in a database at the edge server. The channel prediction engine estimates future vehicle-to-RSU channel gains using these predicted positions. Finally, the resource control engine makes proactive resource control decisions for the vehicles while leveraging the predicted channel gains. Let us now provide a step-by-step overview of the proactive radio resource allocation process within PRISM. The process begins with a data acquisition step, where the position database supplies the most recent vehicle locations to the location prediction engine. Using artificial intelligence-enabled prediction model, the location prediction engine forecasts future positions for each vehicle. These predicted positions are then sent to the channel prediction engine, which integrates them into a digital twin network. By leveraging a high-fidelity, context-aware ray tracing tool, the channel prediction engine estimates the channel gains for all possible vehicle-to-RSU links and forwards them to the resource control engine. The resource control engine uses these predicted channel gains to determine V2I clusters and allocate transmit power. The allocation decisions are then communicated to RSUs, which broadcast the control information to the vehicles. Finally, the vehicles transmit data to their assigned RSUs using the designated subchannels and allocated power. In addition, the contextual information from the physical IoV network is periodically collected and stored in the context database. Now let's take a closer look at the location prediction engine. Predicting a vehicle's future position based on past locations is a classic time series forecasting problem. To tackle this, we use a multi-layer, long, short-term memory recurrent neural network, trained offline with realistic mobility datasets. However, real-world Internet of Vehicles scenarios are dynamic. Road conditions change, traffic patterns shift, and an offline trained model may struggle to keep up. When this happens, inaccurate location predictions can impact channel gain estimation and resource allocation. To overcome this challenge, we introduce an online adaptation mechanism powered by transfer learning. Instead of relying on a static model, our approach periodically updates the LSTM model with new mobility data, ensuring that predictions remain accurate even in evolving environments. Our location prediction engine achieves highly accurate vehicle position forecasts in dynamic IoV networks, with a mean prediction error of less than 0.5 meters. Moreover, by integrating transfer learning, we enhance the model's adaptability, improving location prediction accuracy by at least 3 to 4 times compared to a static approach. Now let's explore our channel prediction engine. The channel prediction engine leverages a digital twin network and a ray tracing tool to replicate RF propagation in V2I communications, accounting for path loss, shadowing, and multipath propagation. To maintain an accurate representation of the dynamic IoV network, it continuously updates its digital twin using real-time network and environmental data from a context database. The channel prediction engine is constructed using the following 4 steps. First, virtual antenna arrays for transmitters and receivers are generated. Next, a virtual deployment scenario is created, incorporating 3D buildings, terrain profiles, and electromagnetic properties of objects. Subsequently, road areas and dimensions are defined, RSUs are placed alongside roads, and vehicles are positioned accordingly. Vehicle mobility is replicated by updating their positions based on the location prediction engine's output. Finally, ray tracing profiles between vehicles and RSUs are computed to model multipath RF propagation. To achieve efficient and precise ray tracing, we utilize the NVIDIA Sionna platform, which leverages GPU-accelerated parallel processing. The final output of the channel prediction engine is a channel gain delay profile, providing both the complex gain and delay of multipath components. The complex channel gain between a vehicle and an RSU is derived from this profile. Next, we introduce our resource control engine. This engine proactively manages vehicle clustering and transmit power allocation for V2I links, allowing clustered vehicles to share the same subchannel for uplink data transmission. However, jointly optimizing vehicle clustering and power allocation is a computationally intractable NP-hard optimization problem. To tackle this challenge, our resource control engine strategically decomposes the optimization problem into 2 manageable subproblems. Our resource control engine uses a heuristic algorithm for V2I clustering and a digital twin-assisted multi-agent Q-learning algorithm for transmit power allocation. These algorithms operate with polynomial complexity while achieving near-optimal performance, ensuring efficient and scalable resource management. Our evaluation setup exploits a simple street canyon scene imported from NVIDIA Sionna, where an IoV network spanning 180 meters by 120 meters is created. The network comprises 3 20-meter-wide road segments, with 4 RSUs strategically placed along the roadside and 30 vehicles deployed on the road. The antenna configurations of both RSU and vehicles are detailed in the accompanying tables. A realistic mobility dataset replicates vehicle movement within the scene. Furthermore, 6 tall buildings of varying dimensions are included to simulate realistic RF propagation phenomena, such as reflection, scattering, and diffraction in an urban street canyon environment. In the created scene, at each time step, vehicle positions are updated based on the mobility dataset, and ray tracing is performed to compute channel gains. To ensure scalability, ray tracing parameters are carefully selected to balance accuracy with computational complexity. Here we compare PRISM's performance with 3 proactive radio resource management schemes, one with perfect future vehicle positions, one without any position prediction, and one without digital twin-enabled channel prediction. The left side figure shows that PRISM achieves nearly the same capacity as an ideal scheme that perfectly knows all the vehicle's future positions well in advance. This figure also shows that omitting location prediction leads to a roughly 33% reduction in performance, as the scheme then relies on the channel state information reported in the previous time step that quickly becomes obsolete in dynamic IoV networks. Similarly, the right side figure reveals that excluding the digital twin for channel prediction also significantly diminishes the achievable capacity. Together, these results confirm that accurate location and channel gain predictions are critical for optimal proactive resource allocation in dynamic IoV networks. To further illustrate the advantage of high-fidelity digital twins for channel prediction, we compare the PRISM with a proactive radio resource management scheme that employs a model-based digital twin. The model-based digital twin uses the vehicle's predicted positions into a standard 3GPP probabilistic path loss model to compute the channel gains between vehicles and roadside units. Unlike the high-fidelity digital twin, which leverages detailed 3D maps and the electromagnetic properties of materials, The model-based digital twin relies solely on statistical network properties. As a result, it tends to overestimate path losses in line-of-sight scenarios and underestimate them in non-line-of-sight conditions. The inaccurate channel estimation leads to suboptimal proactive resource allocation in dynamic IoV networks. The simulation result shows that PRISM with a high-fidelity digital twin achieves system capacities ranging from 200 to 240 megabits per second, compared to 130 to 160 megabits per second with the model-based digital twin. In this video, we demonstrate PRISM, a digital twin and AI-empowered proactive radio resource management framework designed to manage interference and enhance spectrum utilization in dynamic Internet of Vehicle networks. Our framework is versatile and can also be applied to other challenging environments, such as vehicle platooning, urban air mobility, and tactical networks, where real-time information collection from physical networks is difficult. For further details, please refer to our paper published in IEEE Transactions on Network and Service Management, and feel free to reach out. Thank you for watching this demonstration.